Hello and welcome. In this lecture segment, we will talk about the Fiat Shamir transform. And the recommended read for this segment is still Katz-Lindell, chapter 12.5. Last time, we have talked about identification schemes, and you might have wondered already how identification schemes relate to signature schemes. Well, on the one hand side, signature schemes immediately yield identification schemes. How is this so? Well, let's take ourselves a signature scheme and consider the following construction. First, we generate verification key and secret key or signing key for the signature scheme. And we provide the prover of our identification scheme with a signing key and the verifier with the verification key. So in the first message, recall that we defined identification schemes to have 3 rounds. And the first message from the prover to the verifier is just empty. But since by the syntax of identification schemes require a message I, we just send 1 as this message. So next, the verifier just chooses a uniformly random string R and sends R back to the prover. The prover computes a signature on R and sends the signature back to the verifier. And now the verifier just verifies if sigma is a valid signature on this random message R, and if so, it accepts. Why did we have to send a 1 in the first round? Well, recall that the verifier test checks if the output of the V algorithm is I, and I is the first message of the prover. So this is 1 here. It follows routinely that if the signature scheme is EUF-CMA secure, then this identification scheme is also secure, or we didn't give the security of identification schemes a specific name, but yeah, this identification scheme will be secure. But what about the converse? Can we somehow build signature schemes from identification schemes? Well, let's take ourselves an identification scheme. Consider the following idea or the following strategy. We will somehow let the prover choose the challenge R, which is normally computed by the verifier, by himself to collapse this 3-round protocol into a 1-message protocol. Obviously, this is plainly insecure if we let the prover choose this message R freely, or this challenge R freely. Recall that in the last lecture in Schnorr's protocol, we've actually simulated the transcript oracle by having the ability to choose this R freely, or to choose this R depending on other values that are computed in the protocol. So the idea of Fiat and Shamir was to make this challenge R a function of the first message I and a message M that we want to sign. So obviously this function should be unpredictable for every new I and M for which we didn't compute it yet. So let's take ourselves an identification scheme. And the proposal of Fiat and Shamir was to use a hash function as this function, which maps a pair of first message and the message we want to sign into such a challenge R. So the Fiat Shamir transform gen prime sign prime verify prime of this identification scheme gen p1 p2 v is given as follows. The gen prime function just computes or just runs the gen algorithm of the identification scheme, and it sets the verification key to the public key of the identification key and leaves the secret key B. The sign algorithm works as follows. So first we compute the first round, the first message of the identification scheme. We run P1 of SK, obtaining a message I and a state ST. Next, we hash I and the message M using the hash function H, obtaining a string R. Finally, we compute S as via the second prover algorithm by running it on the secret key SK, the state ST, and this string R. And the signature consists of I, R, and S. How do we verify? Well, given a verification key, a message M, and such a signature sigma equals IRS, if it holds that V of PK, R, and S equals I, that's the verifier algorithm for the identification scheme, and R equals the hash of I and M, then we accept, otherwise we reject. To this protocol, there is a small improvement, really just a tiny improvement. Note that I is computed by, or can be computed from PK, R, and S. So instead of running this check that V equals, or V of PK, R, and S equals I, we just compute I this way, right? So we can likewise compute I via V of PK, R, and S. And then we don't have to include I into the signature. So this is just a small improvement, but for the security proof, we will stay with the original form of this protocol, which will make a few things easier or will just make a few things easier to write in the security proof. Completeness of this protocol obviously follows immediately from the completeness of the underlying identification scheme. So we leave that as an exercise. And we go directly to the security proof of this construction. So assume that gen P1, P2, V is a secure identification scheme, and further assume that H is modeled as a random oracle. Then gen prime, sign prime, verify prime is an EUF CMA secure signature scheme. So our proof starts like almost every other proof in this lecture. Let A be a PPT adversary with non-negligible advantage epsilon against the EUF CMA security of our scheme, against the EUF CMA security of gen prime, sign prime, and verify prime. That is, it holds that probability that A wins this EUF CMA experiment is greater or equal epsilon. As always, let's first write down this experiment with the actual algorithms of the scheme. So On the left side, as always, we have our adversary A. And the experiment first, well, generates PKSK using the gen algorithm and provides the verification key, which is PK, to the adversary. Next, the adversary gets access to a signing oracle, which it queries with messages MJ. And how do we compute signatures? Well, first compute IJ and the state ST via the P1 algorithm, gets P1 of SK. Next, RJ is computed via the hash function H, which is, for the sake of this proof, a random oracle. It's H of IJ MJ. SJ is computed as P2 of SK, ST, and RJ. And finally, the signature sigma j just consists of IJ, RJ, and SJ. Okay, so this is our signing oracle for this scheme. Adversary gets sigma j. Now, of course, as always in the random oracle model, we also need to grant the adversary access to the random oracle. Let's call the queries of the adversary to the random oracle the M prime I. And he receives, let's call this HI prime. Now, at some point, the adversary outputs a forge message M asked together with a signature. Let's already call this I asked, R asked, and S asked. And the adversary wins if V of PK I asked, R asked, and S asked equals pardon me, of course the I asked is here, make this a little bit smaller, V of PK R asked S asked equals I asked, and H of I asked M equals R asked. Okay, so this is the EU-FCMA experiment. Let's maybe write output 1. Output 1. This is the EU-FCMA experiment for our scheme. Okay, so as always, when we work in the random oracle model, we need a bound on the number of queries that our adversary A makes to the random oracle. So assume A makes at most Q, which is polynomial in the security parameter queries to the random oracle H. To the random oracle H. Furthermore, we make the following simplifying assumptions. We also make the following simplifying assumptions. These are just assumptions on the behavior of A. So these assumptions are really without loss of generality, but they will allow us to write down our reduction a little bit more compact than if we were to just allow a general A. So the first simplification is that A sends each random oracle query only once. Right? This is not really a restriction because every adversary who queries the random oracle several times on the same input could just simulate further queries by storing such a query and then just repeating it when the internal adversary asks the same query again. Okay. Further, we assume the random oracle queries of A are of the form let's say II and MI prime. Let's call it II prime and MI prime. That is, it only makes queries of the form that we actually use in the protocol. If it makes queries that don't start with such an II prime, then obviously it won't be able to use such queries to make a forge later. And finally, third simplifying assumption, if A queries the signing oracle with a message MJ, and obtains a signature sigma j, which is ij, rj, and sj, then it will not query the random oracle H on ij, on the input ij, mj. Why? Well, the signature sigma j contains rj, which is the output of the random oracle. So in effect, if A obtains a signature on mj, it kind of has queried the random oracle already on ij, mj, right? Or it can just remember ij, mj as the input to the random oracle, which leads to rj. So there's no need, in fact, that A queries the random oracle on this input. So now that we have set down or laid out these assumptions, we will now construct an adversary A prime, which breaks the security of the underlying identification protocol gen P1, P2, V with probability epsilon divided by Q. We will now construct an adversary A prime which breaks security of gen P1, P2, V with probability epsilon divided by Q. Of course, since epsilon is non-negligible and Q is polynomial, this will also be non-negligible. So how does A prime look? As always, A prime will simulate, in this case, the EUF-CMA experiment. In a first step, it will just choose a uniformly random index I asked in 1 to Q. We've seen something like this already in the proof of theorem 9.1. So here we have our adversary A. And first off, we need to provide A with a verification key. How do we do this? Well, our A prime is an adversary against the identification scheme. So in the first message, it obtains a public key PK. So what does A prime do? It just uses this PK and forwards it to A. Next, we need to simulate a signing oracle to the adversary A. How do we do this? Well, let's say every time A queries the signing oracle with a message MJ, we just take this MJ, or no, differently, we actually just press our transcript button. So here's the transcript oracle, and back comes a transcript IJ, RJ, and SJ. No, it's not so straight. And we just use IJ, RJ, SJ, or we set our signature sigma j to be IJ, RJ, and SJ. And we give the adversary A this sigma j. Now, one more thing left to do, as always in random oracle model proofs, the adversary A wants to have access to the random oracle. And we said he only queries it on queries of the form II prime, comma, MI prime. Now we need to distinguish two cases. So we count these queries, and depending on the index I, if I equals I asked, right? And I asked, recall that's this index up here that we chose uniformly random. So if I equals, or let's say if let's start with the non-equals case. So if I is not equals I asked, we just simulate the random oracle by choosing H prime I uniformly at random. 1 to the security parameter. On the other hand, if I equals I asked, then we do the following. Then first, we take this I, this I prime, and output it as a, or let's call it I asked, and output it as our first message in the challenge protocol now. Upon this, the challenger will answer with a uniformly random R, and we will just set, so this R comes back here, we will just set HI asked, let's maybe erase this, we set HI asked prime, we set it to R. Okay. Good. Now, just one more thing is missing. So now we've simulated the random oracle. HI prime comes back here. At some point, our adversary outputs a forge. M asked, I asked, R asked, and S asked. And if we say that if I asked, comma, M asked equals I asked prime, M I asked prime, that is, if our guess for I asked was correct, if we embedded this H asked at the right position, then we output S asked. Put S asked, otherwise bot, right? So in the last message comes out either S asked or bot. Okay, so this concludes the description of our adversary A prime. Next, let's analyze its advantage or its success probability in breaking the security of the identification protocol Gen P1 P2 V. So first, kind of as always, we observe that from the view of A, it holds that A prime simulates the EUF CMA experiment faithfully. So the things that we have to check is that the signing oracle is simulated faithfully. But this is the case as the RJ are chosen uniformly random and therefore have the correct distribution of random oracle outputs. As the RJ are chosen uniformly random. So that's fine. And pretty much the same holds for the outputs of H. Or same for outputs of the random oracle H. So, as in the proof of theorem 9.1, we can define an event queried. As in the proof of theorem 9.1, we can define an event which I call queried, and I'm defining it by, well, there exists an I bar in 1 to Q such that I asked, M asked equals I prime I bar, M prime I bar. So this is just the event that basically there is an index for an index of a I bar of a random oracle query, which the adversary is later gonna use in his forge. We can argue that if this event queried does not happen, then the adversary only has negligible probability in winning this experiment. So, but I'm not gonna do this again. This is shown in the very same manner as we showed this in theorem 9.1 or in the proof of theorem 9.1 by an application of the law of total probability, and argue that, well, probability that A wins the EUFCMA experiment and the event queried happened is greater than epsilon prime, where this epsilon prime is non-negligible. Okay. Finally, with this we can conclude that, well, the probability that A prime wins the ident experiment is at least, well, probability that A wins the EUF-CMA experiment and the event queried happens, and, well, we guessed correctly. That is, I asked is I bar. And since I asked is chosen uniformly at random and independent of everything else, this event I asked equals I bar is independent of the rest. So we have that this probability is the same as EUFCMA of A equals 1 and queried times probability I asked equals I bar, but this is just 1 over Q. This we know is greater equal epsilon, so this is greater equal epsilon divided by Q, which is non-negligible, but this contradicts the security of the identification scheme. V. And this concludes this proof. In the last lecture, we've seen an identification scheme whose security is based on the discrete logarithm problem, the Schnorr identification scheme. In this lecture, we've seen the Fiat Shamir transform, which allows us to transform any such identification scheme into an EUF CMA secure signature scheme. So combining the Schnorr identification scheme with theorem 9.3, which we just proved, yields the following EUF CMA secure signature scheme. And just for completeness, we're going to write it out. So again, we assume that G is a cryptographic group with prime order P and a generator G. And H mapping from 0, 1 ast to ZP is a hash function. Then the Schnorr signature scheme gen sign verify is given as follows. So gen just chooses X uniformly at random from ZP. We compute Y as G to the X. And we output a verification key Y and a signing key X. To sign a message M using the signing key X, we choose a uniformly random K in ZP. We compute I as G to the K. Next, we compute R as the hash of I and M. And we set S to R times X plus K modulo P. And we output R, the signature R and S. To verify a signature sigma RS equals RS for a message M under a verification key Y, we first compute I as G to the S times Y to the minus R. And next we check if R equals H of IM. So if we hash this I together with M, do we get R? If so, we output 1, otherwise 0. Correctness of this scheme naturally follows from the correctness of the Fiat Shamir transform and the correctness of Schnorr's identification scheme, since this is just theorem 9.3 applied to the Schnorr identification scheme. So here's a picture of Klaus-Peter Schnorr. His signatures are basically the most efficient and shortest signatures when we instantiate them with elliptic curve groups. In practice, this group G, this elliptic curve group G, its order P and the generator G are publicly fixed. We take an elliptic curve or an elliptic curve group such as at 25519. Here's a reference to this specific group choice. But for this group, the size of both the verification and signing keys is 256 bits or 32 bytes. That's really a rather short string. 32 bytes you could think of as the length of a password. So here the signing keys are in fact short enough to store them, say, like in a human readable password. The size of the signatures is twice as long. It's 512 bits or equivalently 64 bytes, which is also still quite short. To compute signing, we have to do just a single exponentiation, and for verification, we need to do 2 exponentiations. So this is really, in practical terms, a great signature scheme, and one might ask, why is this not used all over the place? So if this is news to you, this scheme has not received widespread use. And why is this the case? Why are Schnorr signatures not widely used? The answer is intellectual property rights. So before Klaus-Peter Schnorr published this scheme, he filed for a US patent, available here, and he held this patent until 2008. So until 2008, if you wanted to use this scheme, you would have to pay him royalty fees. And of course, this is the best way to prevent any invention to be used or to be adapted in a standard is by patenting it and by forcing companies that want to use it to pay you royalties. So what happened instead is that a variant of the Schnorr signature scheme was standardized by NIST, the so-called digital signature algorithm. So again, let G be a cryptographic group, and now we take ourselves two hash functions, both of which are modeled as random oracles in the proof. The DSA scheme, gen, sign, and verify, is given as follows. Gen is exactly the same as for the Schnorr signature scheme, that we choose X uniformly random from ZP, compute Y as G to the X, set the verification key to be Y, and the signing key to be X. To sign a message M, we choose K uniformly at random from ZP. We compute R as F of G to the K, and set S to be K inverse times H of M plus X times R modulo P. If either R equals 0 or S equals 0, we restart this procedure just with retry this with a fresh and uniformly random K, so long until both R and S are not equal 0. But in fact, the probability of this happening is exponentially small. So the algorithm states for this check, but it essentially never happens. Finally, we output a signature sigma, which is R, S. To verify a signature, we first check if both R and S are non-zero, and if it holds that R is equal to F of G to the H of M times S inverse times Y to the R times S inverse. If this check holds, we output 1, otherwise 0. Again, proving completeness of this protocol is rather straightforward, but proving security follows essentially the same ideas of both theorem 9.2 and 9.3. Now, in fact, Klaus-Peter Schnorr thought that this was still too close to his invention and went for a trial or sued NIST over a patent infringement over his patent. But eventually this was apparently settled out of court. Now it's time to wrap up this lecture. We've first discussed that signature schemes immediately imply identification schemes. Conversely, every 3-round identification scheme can be transformed into a signature scheme via the Fiat Shamir transform. The security proof for this is in the random oracle model. Using the Fiat Shamir transform on the Schnorr identification scheme, we obtain Schnorr signatures, the currently most efficient known signature scheme with the shortest signatures, which since 2008 has received somewhat wide adoption, because in 2008 Klaus-Peter Schnorr's patent has expired. Finally, due to patent issues, the slightly more contrived DSA scheme was standardized. And being standardized, this DSA scheme made it into many applications despite being somewhat more contrived and less efficient than Schnorr signatures. On that note, I would like to end this lecture. Thanks everyone for watching.